Good morning, everyone. We're going to continue today with Binomial Theorem Part 2. And remember I said to you, I find this particular topic really cool. So let's take a look at the question that we have right up at the top of the page. And I hope what you're looking at is that exponent of 12. That's the problem. Exponent of 4, 5, 6, 7, 8, not a problem whatsoever because we have access to Pascal's triangle. Remember, row 0 or exponent of 0, row 1, exponent of 1, row 2, exponent of 2, row 3, exponent of 3, row 4, exponent of 4, row 5, exponent of 5. And I could draw it a little bit further, but when you start getting into 12, you don't have time to be drawing Pascal's triangle. So what we're looking at is that a large exponent means a lot of terms. We would know that that would mean 13 terms. And the problem is, what will the numerical coefficients be? I would have to sit here and draw Pascal's triangle until it had a row 13. So based on our knowledge, of yesterday, we would have to draw Pascal's triangle with 12 steps. And this would be a lot of work. There must be a better way. Okay, one more time, now that all my writing's done. One more time. So based on the fact that the exponent is 12, it would mean that there would be 13 terms, and we would have to continue Pascal's triangle 12 full steps to row 13. Okay? So completely unrealistic to do that. Okay. Well, what are we going to do? How are we going to do this? Well, let me show you something really cool. Let me grab a piece of paper here for a second. What if I said to you, 1 choose 0? Number of trials, number of successes. Okay. What about if I said to you, 1 choose 0, 1 choose 1? Okay. What if I said to you, because don't forget, this is row 0, this is row 1, this is row 2. 2 choose 0, 2 choose 1, 2, choose 2. Number of trials, number of successes, number of trials, number of successes, number of trials, number of successes. Row 3. And don't forget, the row indicates the exponent. 3, choose 0. 3, choose 1. 3, choose 2. 3, choose 3. How cool is this? Row 4. Fourth exponent, 5 terms. 4, choose 0. 4, choose 1. 4, choose 2. 4, choose 3. 4, choose 4. How cool is this? Row 5, or fifth exponent. Five, choose 0. 5, choose 1. 5, choose 2, does give you 10. 5, choose 3. 5, choose 4. 5, choose 5. So what we've just discovered is Pascal's triangle is a series of combinations. And it's a series of combinations that we're quite familiar with in terms of number of trials and number of successes. How cool is that? Let's take a look at our example. It says, let's try and find the first 4 terms. Okay, remember, my first term is A. I'm going to go in a descending order. So A to the 12, A to the 11, A to the 10, A to the 9. My second term is 3. I'm going to go in ascending order. 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3. Now, our question always was, what the heck do we do about numerical coefficients? We don't have to worry about that anymore. We don't have to worry about having this memorized at all. Number of trials, number of successes. 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 So let's go through and clean up. 12, choose 0 is 1. A to the 12, 3, choose 0 is 1. 12, choose 1 is 12. A to the 11, 3 to the 1 is 3. 12, choose 2 on our calculator is 66. A to the 10, 3 squared is 9. 12, choose 3 on our calculator is 220. A to the 9 and 3 to the 3 is 27. So when I clean up, 1 times 1 times 80 to the 12, 12 times 3, A to the 11, 66 times 9, A to the 10, oops, 220 times 27, A to the 9. And then you would do all of your other terms. So I don't have to worry anymore of having Pascal's triangle, because really Pascal's triangle is a series of combinations. Okay, when you're ready, let's flip and we'll get into some more examples. Okay? So, what does all of this remind us of? The whole idea of number of trials and number of successes. Well, it reminds us of the whole idea of a Bernoulli trial, but it's reversed. Okay, what do I mean by that? Here's the Bernoulli formula. Number of trials to number of successes, probability of success to the number of successes, probability of failure to the number of failures. That's my Bernoulli formula. Now, let's think of each of the terms. Let's think of each of the terms in my binomial expansion. We've got a combination, number of trials, number of successes. We've got a probability of n minus k. Notice how this is a 12, so that would be your n minus k. So that would be this probability, like what we would call probability of failure. And then you have a probability, you have your final term, which is your second term, which is to the exponent of the k, just like the p. So the formula, what I'm trying to get across here, combination part is the exact same. These two things are reversed. The p and the q are reversed. Now let's take a look at that one more time. Combination part is the same. If this was your n and this was your k, 12 minus 0 is 12, and that would be your k right there. Your p and your q are reversed. Kind of cool. Again, I'm not going to ask you to reiterate that for me. It's just I want to show you how the two relate. Okay, let's take a look at our next example. It says, can you please expand and give me the first 5 terms? So 1, 2, 3, 4, 5. Okay. My x is the first term in my binomial expansion, and 2y, positive 2y, is the second term. Okay. So the exponent is a 9. That would mean in total that there would be 10 terms. So x to the 9, x to the 8, x to the 7, x to the 6, x to the 5. First term is handled. 2y to the 0, 2y to the 1, 2y squared, ascending order now, 2y cubed, 2y to the 4. So first term is descending order, second term is ascending order. Now, the numerical coefficients, we don't have to worry about Pascal's anymore. 9 choose 0, 9 choose 1, 9 choose 2, 9 choose 3, 9 choose 4. Beautiful. Let's clean everything up. 9 choose 0 is 1. X to the 9, 2y to the 0 is 1. 9 choose 1 is 9. X to the 8, 2y to the 1 is 2y. 9 choose 2 is 36. X to the 7, careful, 2y squared is 4y squared. 9 choose 3 is 84. X to the 6, 2y cubed is 8y cubed. 9 choose 4 is 126. X to the 5, 2y to the 4 is 16y4. Keep cleaning up. X to the 9. 9 times 2 is 18, x to the 8. 36 times 4, 144, x to the 7. 84 times 8, 672. Uh-oh, did I make a boo-boo? Yes, I most certainly did. There should be a y here. And there should be a y to the 4 here. No, there's a mistake. Come right back up here, guys. Sorry. Okay. 9 choose 2 is 36. X to the 7 is x to the 7. 2y squared is 4y squared. So that's going to be, let's go through this one more time. Sorry about that. 1 times x to the 9 times 1 is x to the 9. 9 times 2 is 18, x to the 8y. 36 times 4 is 144, x to the 7, y squared. 84 times 8 is 672, x to the 6, y cubed. And 126 times 16 is 2016, x to the 5, y to the 4. Sorry about that. The error was right here and right there. Okay, please take a moment. Let me give you a moment so that's rectified. Sorry about that, guys. This was going too fast. Okay, so now that we have an idea of a binomial expansion, the first term being the descending power, the second term being the ascending power, and how to get the numerical coefficient using combinations, we're going to take a little twist and we're going to talk about what they call the general term. Okay? And this is going to be a really important question. Now, before we jump into the formula and whatnot, just come down and look at the example. Find the third term in this particular binomial. So when they're asking you for a specific term, so find the third term, they actually want to know the name of the third term. They don't care about the first, they don't care about the second, they don't care about any others. They just want to know the name of the third term. Well, according to what we've been doing in our previous examples, we've been finding out names for multiple terms. I found out the names of the first 5 terms. So if you're just looking for a particular term number, this is the formula that we're going to use. Okay, so now let's dissect the parts in that formula. The A represents the first term in the binomial. Okay. The B represents the second term in the binomial. Okay. The N represents the exponent. Okay. The R starts at 0 for the first term. Okay, now hold on. What do I mean for that? And your R is your N being the exponent minus 1. So if your first term, your R is 0. For your second term, your R is 1. For your third term, your R is 2. For your fourth term, your R is 3, and so on. Okay, let's jump in. The best way to do these is to jump right in. I'm going to write down my formula. And I'm going to look for term number 3. Okay. Now, this N right here is your term number. It's not your exponent. This n right here is your actual exponent. So be careful of that, okay? Be very, very careful. This n right here is your actual term number. I'm looking for term 3. This n right here is the actual exponent in the question. So hold on, the exponent in the question is a 9, and my r value is 1 less than my term number. So my r value is going to be 2. Now think about that. That causes some people a little bit of grief, okay? But come right up here for a second and look at your third term. 1, 2, 3. Now look at the combination for the third term. 9, choose 2. Look at the combination for the second term. 9, choose 1. Look at the combination for the first term. 9, choose 0. That's because we start with a row of 0 in Pascal's. This is always going to be 1 less than the term number. That's what this means. 1 less than the term number.